All right, hello chemists. In this video, we will talk about neutralization and the basics of titrations. A neutralization reaction is a reaction where a Bronsted-Lowry acid and base react to neutralize one another. Note that acids contain hydrogen ions and bases contain hydroxide. In the neutralization reaction formula, an H+ ion will react with a hydroxide ion. The result will be one particle of water, HOH. In addition, the metal cation and anion will react to form salt. So in a neutralization reaction, the products will be water and salt. For example, if a strong acid and a strong base, hydrochloric acid, reacts with sodium hydroxide, one hydrogen ion will react and combine with one OH hydroxide ion to form one HOH water particle, and the salt will be sodium chloride. Note that sodium chloride is aqueous in solution according to our solubility rules. In another strong acid, strong base neutralization reaction, sulfuric acid can react and neutralize potassium hydroxide. In this case, two H's and two OH hydroxide ions will form two water particles. The resulting salt would be potassium K2SO4 sulfate, potassium sulfate. Thirdly, phosphoric acid can neutralize calcium hydroxide, acid with base, by taking 6 hydrogen ions for 3 hydroxide ions and forming 6 H2O water particles, and calcium phosphate, Ca3PO4 2. In neutralization reactions, water and salt is formed. The resulting pH that occurs when the amount of hydroxide ions and H+ ions are equal to each other would be what pH? You guessed it, it would be a neutral pH equal to 7. Again, this is true for strong acids reacting with strong bases. Now, these neutralization reactions actually can be carried out in controlled settings. So titration is the controlled neutralization of acids reacting with bases. Now, we want to emphasize the idea of controlled because in the chemical laboratory or in industry, or perhaps if you're working for some sort of food company or local government studying water supplies, you would need to be familiar with the idea of doing and performing titrations. And performing them means that they are controlled. And so the basic idea of a titration is we will try to analyze an unknown concentration, say, for instance, an unknown acid. That unknown acid would be placed into our Erlenmeyer flask. Because we're attempting to figure out the concentration of the unknown molarity of that acid, we are going to call that, what we're titrating, we call it the analyte because we're analyzing it. And the cool part is that we get to use a fancy piece of lab equipment known as a burette. Burettes allow for very slow, controlled amounts and quantities of acids or bases to be released by the opening and closing of this valve known as the stopcock. Okay. Now, to get a titration to fully work properly, we need to know when to stop adding base to the acid such that we've reached the equivalence point where the hydrogen ion concentration and hydroxide ion concentration are equal, or our resulting solution has been neutralized. So when do we stop it? Well, we would only know that if we could see and visualize a color change. So we need an indicator solution. The most common one would be phenolphthalein. Phenolphthalein on the inside of the acid at the beginning will be colorless. However, as we approach the equivalence point or the neutralization, we will start to see a color change take place. And once the color turns to a light, now I'm going to draw this. This is a dark pink, but in real life, you'd want this to be a light pink. Once you see that light pink, it is approximately the point at which the hydrogen ions and hydroxides are equal and the resulting solution has been neutralized. At that point, you can stop your titration and you can analyze and figure out what the unknown concentration is. Okay, so just a closer look at these neutralization reactions. Remember, we can express double replacement reactions in solutions with molecular, complete, and net ionic equations. Now, the molecular equation will show you that the salt and water particle is formed as two products. Now, if we break down the complete ionic equation by showing which ions are aqueous in solution, you would see that the sodium ions and the chloride ions are not changing their state of matter, but the hydrogen ions and hydroxides are. So we want to remove those spectator ions, and we would want to note that the hydrogen and hydroxide are combining to form water. But ultimately, the resulting solution contains water and our sodium and chloride ions. And so that is the idea of neutralization. Okay, so a little bit more on titration. Again, it's the controlled neutralization. The equivalence point is going to be when the moles of acid and base are equal. That's only going to be really a true statement when the formulas of the acid and bases contain the same number of H plus and OH hydroxide ions. It's going to change just a little bit here if these number of H's and number of hydroxides are different. So just as a practice, how many moles of hydrochloric does it take to neutralize 2.00 moles of sodium hydroxide? Well, according to our equation, they have to be equal to each other to neutralize each other. So the answer would be 2.00 moles of hydrochloric acid are required to neutralize 2.00 moles of sodium hydroxide. And in the formula, there is one H and one OH. So our formula will work for us. Now, if that's not true, such as in our next question, we're going to make a slight modification. How many moles of sulfuric acid does it take to neutralize 2.00 moles of sodium hydroxide? In this case, we would note that in the left side of the equation, we're going to insert the number 2 for the fact that there's 2 H's for every particle of sulfuric acid. Now multiply that by the moles of acid, since that's our unknown in the question, how many moles of it? So then we'll insert to the right side of our equation the number of hydroxide ions in the formula of sodium hydroxide is just 1. There's only one of those in that particle, right? And then multiply that by the quantity 2.00 moles. So how many moles of the acid does it take to neutralize this base? Well, if you do the math here, the answer would be 1. And if we're using our rules of sig figs, the moles of acid would be 1.00 moles. Now, if we think about it, that actually makes sense because in 1 mole of this acid, given that each particle contains 2 hydrogens, that would ultimately end up giving us an equal quantity of H plus ions inside of 2 moles of sodium hydroxide. So our H plus and OH minus ions would be at a neutralization point. Now, next would be titration curves, and these are interesting because what we're evaluating is the change in pH. And we can also measure pH during titrations through use of a pH probe, a handy piece of equipment. So if we're titrating a strong acid with a strong base, this is the resulting curve for that titration. It's basically designed to show us how the pH changes over time as we add in more and more and more of our titrant, or more and more of our base as it trips down into the Erlenmeyer flask. At the very beginning in section 1 of the graph, it starts off with a pH around 1. Well, that would make sense because the pH of a strong acid is really low. It's a lot less than 7 for acidic solutions. But as we begin to add 5, 10, 15 milliliters of base, we start creeping up in our pH. pH will rise as the amount of acid begins to be neutralized by the base. And then at some point near the equivalence, the pH will rise rapidly. And in the middle of that rise, we'll note that this is the equivalence point. And at the equivalence point, we're going to see that change of the phenolphthalein from colorless to a light pink. And then the pH at that equivalence point, when the H plus ions and the hydroxides are equal, we're going to see that that resulting pH is neutral around 7. Then if we were to keep adding the titrant, then we would be in presence of excess base, which would be a pH greater than 7. Okay, so final few ideas and then a couple practice problems to make sure we grasp and master titration is that in lab, moles are not very convenient. So this equation here, while it does work, it's not super user-friendly for a chemist in the lab because you really can't measure moles at all. Measuring moles would be the same as counting particles, and particles are too small to count, so therefore it's not super easy to use. So instead, we modify the equation to make it useful for lab purposes or to make it useful for titrations. And so to do that, we need to understand that molarity is equal to the moles. I'm going to represent moles with an N divided by the moles of solute divided by the volume of solution. Rearranging this equation for N, or moles, we would multiply both sides by volume, and volume will cancel on the right. Now that we can see N is equal to M times V. And so moles of acid will now be restated as molarity of the acid times the volume of the acid. And the moles of the base at the equivalence will be restated as the molarity of the base times the volume of the base. This is much more user-friendly to us. Molarities and volumes can be measured, whereas moles really can't. This equation might look useful to you, or it might look similar to you from our solutions equation where we did dilutions. Remember the idea that M1V1 is equal to M2V2, or if you learned MCVC, is equal to MdVd. So same idea applies to titration. All right, now we do need to keep in mind that the number of H plus ions should multiply by the moles of acid, and the number of hydroxides should multiply by the moles of the base, if they're not equal in the chemical formulas. All right, MaVa equals MibVib. That is how I remember the equation. MaVa equals MibVib. It is our titration equation. Okay, let's just do one or two to get the idea. How many milliliters of a 0.100 molar sodium hydroxide solution are needed to neutralize 20.00 milliliters of a 0.500 molar hydrochloric acid solution? So in this problem, the sodium hydroxide is the analyte and the HCl is the titrant. Okay. So let's go ahead and use our MaVa equals MibVib equation. And on the left side of the equation, we will plug in the number of H plus ions in our acid is just 1H times the molarity of that acid is 0.500. And the volume of the acid at neutralization was 20.00. And on the right side of the equation, the hydroxide ions in the formula is just 1 OH. The molarity of the base is 0.100. And we are solving for the volume of the base needed for that neutralization to take place. Well, a little bit of algebra will tell us to divide by 1 times 0.100. What I do to the right, I do to the left. The volume of the base will then be equal to 100 decimal point milliliters. In keeping with sig figs, I'm going to be looking at the idea that there's 3 sig figs here, there's 3 here, and there's 4 here. So we will maintain 3 sig figs. 100 with a decimal point will then contain 3 sig figs. All right, I know I can hear you screaming through the video. These numbers contain 1 sig fig. Why doesn't our answer have 1 sig fig? Well, these numbers actually don't contain 1 sig fig. They contain an infinite number, excuse me, of sig figs. They're just counting numbers. We're counting the number of H's and OH's. There is no precision involved there. It's an exact amount, whereas measurements have limitations, and that's why we use sig figs for those numbers. So just ignore the sig figs, or ignore those numbers when it comes to sig figs. Okay, first one done. Let's go for number 2. It takes 45 milliliters of 2.0 molar sulfuric to completely neutralize 30 milliliters of sodium hydroxide solution. What's the molarity of the base? Kind of liked that color pink. Let's use that one. All right, in this case, the acid contains 2 H pluses in the formula. We will insert 2, and now we will begin MAVA. The molarity of the acid is 2.0, multiplied by the volume 45.0. The number of hydroxides in sodium hydroxide is 1. MibVib, we will solve for the molarity of the base at neutralization by multiplying by 30.0 milliliters for the volume of the base. A little bit of algebra never hurt. Divide both sides by 1 times 30.0. And we will end up with the concentration of the base at the equivalence point is equal to 6. And if we are discussing sig figs here, we should ignore these counting numbers and focus on this one, 3, 2, and 3. So we will go with 2 sig figs, which would require us to say 6.0 molar is the concentration of our sodium hydroxide solution. Congratulations, you have done it. I would maybe encourage you guys to try number 3 on your own. All right, hope it helped. And as always, if you have any questions, please see your chemistry teacher.